So DPC is an iterative algorithm, and what that means is that we have to keep doing it over a number of iterations in order to see if we're going to converge on power levels that'll give us the right signal to interference ratios. And that's the exact opposite of the single step TPC algorithm, which was just plug into the equation once and then you get the answer that you're looking for. Here we're gonna have to calculate it, get the new power levels, calculate it again, get the new power levels, and so on, keep updating it. And so in order to start, we have to choose an initial set of power levels. And I'm going to say that we're going to start this whole thing assuming that each of the transmitters have a power level of 2 milliwatts. And so as we go through this, we will see how this comes into play and how these power levels change in each iteration as we go along. So given that we're starting at 2 milliwatts, then we can use that to calculate the initial signal to interference ratios. And so first thing we have to say is how do we get each of these values that's in the SIR equation? The SIR is equal to the signal divided by the interference plus the noise. And so we'll start off with link 1. And for link 1, the signal is the direct channel gain, which is 0.9, which is 0.9, times the initial transmit power, which is 2 milliwatts. 2 milliwatts, which that's basically saying that we have 90% of that 2 milliwatts actually getting to the receiver. And then the interference is going to be how each of these other transmitters, transmitters 2 and transmitters 3, couple into receiver 1. So for transmitter 2, that's 0.1. So 10% times that power, which is 2 milliwatts, again, because they're all starting at the same power, plus 0.2, which is that for receiver 3, 0.2 times 2 milliwatts. And then we have to add the noise part of it, which is this this 0.1 over here. And if we do that calculation out, we get about 2.57. So right now we're 2.57 times higher than the desired signal is 2.57 times higher than the interfering portion. And so if we compare that to our target of 1.8, we see that we're too high. And so we expect that transmitter 1 is going to decrease its power. And so now similarly we can look at transmitter 2. And for transmitter 2, the direct gain is 0.8. So we take 0.8, multiply that by 2 milliwatts, divided by the interference, which comes from receivers 1 and receivers 3. So we take 0.1 times 2 milliwatts plus 0.1 again, because both of these indirect gains are 0.1 in this case, times 2 milliwatts, plus the receiver noise, which is 0.2 for this guy. And we get about 2.67, which again is higher. And if we repeat the same calculations for the third one, we have 0.9, which is the direct gain for 3, times 2 milliwatts. And then the interference are these factors of 0.2 over here. So we take 0.2 times 2 plus 0.2 times 2 plus the noise, which is 0.3. And we get 1.64. So as you can see, while these two are higher than their respective targets, this one's higher by 1.8 compared to 2.57. This one's higher by about 0.67. But this one's lower by about 0.6, 1.64 as opposed to the 2.2. So we expect these two transmit powers to go up, or sorry, these two transmit powers to go down, and this transmit power to go up in order to compensate for that.